let's go ahead and put down our master energy equation, the one that you should be well familiar with for Thursday. And go ahead and put in all the terms that would be relevant. So we have potential energy, and then kinetic energy, and I'm going to address it as total kinetic energy. I'm going to have two different varieties of it in general. I'm going to realize that these things both roll, so I'm going to approximate that the energy loss to the environment is minimal. And then I'm going to, of course, keep track of these energies at the end. Looks like that. Okay, what might be a good place to set my potential energy 0 in this problem? The bottom. I always want to set it the lowest head of interest. That means that the final potential energy is 0, and the initial, of course, is mgh. If you set it at the lowest head of interest, you don't have to deal with negative heights, because that's annoying. Of course, they also start at rest, so there's no kinetic energy to start with, so the only place you can find energy at the beginning is in storage. They both have energy in storage. Notice, by the way, I'm trying to not say something that would be true for only one of them, because I want to work smarter, not harder, right? I want to put in as many things as I can that are true for both of them, because the moment I commit to something that's true about the disk versus the ring, I have twice as much work to do, because I have to do 2 columns. At the end, we're going to find that the energy, of course, is split between the 2 forms. And I just did a lot of legwork there to, of course, find out what that would be when you're rolling. And I guess I can go ahead and put in here as well. Well, let me copy a new line. Here's my final kinetic energy. So, still haven't said anything that's true for one but not the other, so I'm going to continue to keep my calculation together. The mass cancels, and then I can solve for VCOM at the end. And I get this. Now at this point, I have the answer in terms of G, which is always allowed. I have H initial, which was a given. The only thing I have left to do now is to specify what's true for disk versus the ring, which is with squiggle. And so at this point, I'm going to split it off into 2 pieces. I'm going to talk about the disk and the ring. So this is where I go to the table, the 2nd page of the formula sheet, look up the rotational inertias when they're rotating around the center of masses, which is what they're doing. And the formula sheet will tell me that this is 1/2 mr squared, and this is mr squared. So just as a reminder, the ring had a larger rotational inertia. The reason why is why? Why is that? All else being equal. The mass is all on the outside of a ring, right? Whereas it's uniformly distributed from the middle out to the edge for a disk. So our squiggle factors, they're right in the front. Squiggle here is 1/2. And then there's nothing here, so squiggle is 1. So the squiggle factor enters in, and we can just go ahead and sub in and see what we get. I guess let's start with the ring. VCOM final, square root of 2g h initial, 1 plus 1. So what do we get? We get 1 plus 1 is 2, cancels with this 2, we get square root of g h initial. That, of course, by itself is not terribly meaningful. You could certainly, if you had h initial as a number, you could get the VCOM final as a number as well. But I'm interested in comparing the two. So that's just my baseline that I'm going to compare the other one to that I haven't done yet. Let me go ahead and put that in. Now squiggle the half. 1 plus a half, that's 3 halves. 2 divided by 3 halves is 4/3. Like that. And in case your intuition about square roots of fractions is not the greatest, square root of 4/3 is about 1.15. So 1.15, that's bigger, right? It's 1.15 times the previous answer, so this is 15% faster. So the disk arrives at the base of the incline going 15% faster than the ring. And of course, we also reasoned that if it gets there with a faster speed, it also got there earlier. Okay? So let's try it. I have this with me. Make some space here. Here I have my racetrack. I have my contestants. I have my disc and my ring. And I'm going to put them both at the top of the incline. We'll see who wins the race. Let's try it. Going to put them here. Going to start them off nice and fair. Whoops. Does the disc win? Okay. So it worked out the way that we computed. Now that's the mathematical way. You can also reason this conceptually. So let me tell you how. Okay. So these are our two contestants. We found that this one has a relatively small rotational inertia because the mass is more in. This has a larger rotational inertia. So it's the difference between this, okay, versus this, right? So if you think about it, this is the rotational version of something that you may have seen in the linear world. So if you go out to the playground, you see like a little wiry kid, and they're going to have a foot race with the biggest kid in the class. Okay, you know who's going to win that race. Okay, the little scrawny kid is out of there, right? The big kid just is harder to get going, so it takes longer. This is the rotational version. So this thing has lots of rotational inertia, and this is comparatively more nimble. Just goes out of there. Okay? So what happens is, if you talk about the initial allotment of energy that they both have, they don't spend it the same way. If you have a lot of rotational inertia, I guess let me put it next to the disk. So the disk is the one that spends less energy in rotation, and so therefore has more to spend in translation. Okay? You can see it right here, right? The squiggle factor is what determines how much of your energy is in rotation. Okay? So if you have a smaller squiggle factor, then this will be smaller. And likewise over here for the ring, it can have exactly the same allotment of potential energy, but is going to have to spend more energy towards rotation, and so therefore has less available for translation. So it basically has to use up a higher proportion of its energy towards rotating, and so has less for going forward. Okay? So that right there is kind of the conceptual reasoning, is that if you have a small rotational inertia, you will generally go faster. It's right in the equation, by the way. Look at the equation. Squiggle is in the denominator. If squiggle is larger, well, remember, squiggle is the factor in front of the rotational inertia. So if squiggle is larger, that makes the rotational inertia larger. Well, it's in the denominator, so that's going to make vcom slower. So notice that predicting out of our equation is that larger rotational inertia will actually hurt you in the race. Okay? The larger the rotational inertia is, the slower you will go. So you can race a bunch of objects down and realize that the more something has rotational inertia, the more energy it's going to have to take for its rotation, a larger proportion of its initial energy, and the less it will have to spend on the translation, the actual moving down the track. Okay. I guess the other thing that I should mention is that the actual mass of the object long ago canceled. It canceled right here. So it doesn't actually matter if they're the same mass. I said that they did, but it doesn't actually matter. Okay, why is that? Well, if you have more mass, you certainly have more energy to spend, right? MGH is larger, but then you also have more kinetic energy, right? So if you have more mass, yes, you get a larger pool of initial energy, but then the proportion which you have to spend towards each one is still determined by your squiggle value, okay? So you can see it canceling out right here. Anytime you see something that's missing from the answer that you're surprised perhaps by, you just go back and see where it canceled and reason out what happened. If you have more mass, yes, you need more kinetic energy to go a certain speed, but you automatically get more mass by just being there at that height, okay? The other thing that canceled was the radius. So they don't even have to be the same radius. Now, if you're wondering where that canceled, it's canceled right back here. So you may be saying, if you have a larger radius, doesn't that increase your rotational inertia? Sure. Okay. If your radius is larger, that's going to increase your rotational inertia. You're bigger. You have more rotational inertia, but guess what? You also get to rotate slower at the same speed. Okay? So if you've ever seen, for instance, a gigantic wheel and a small wheel both moving at the same speed, obviously the big wheel gets to rotate a lot slower in comparison. So that might look like this. Okay? I guess you can try throwing a skateboard wheel out of a car and you can see how fast it would have to rotate to keep up with you. So that's of course why they tend to have larger wheels in faster moving vehicles, right? Yes? Okay, so again, it comes out in the wash. If you have a larger radius, yes, you have more rotational inertia, but you also get to rotate slower. So if this increases and this decreases, there's no effect on this. So what we find is that the only surviving factor of the rotational inertia was squiggle mr squared. And yet the only factor that survives the answer was squiggle. The mass canceled, the radius canceled, so the only factor that survived was squiggle, and squiggle has to do with mass distribution, okay? So the only thing that matters is the mass distribution, not the absolute mass, not the absolute radius, but how that mass is distributed along that radius. So if you want, you can rummage through your garage, you can find any disk will be any ring. It doesn't matter if they're the same mass, it doesn't matter if they're the same radius. What matters is simply mass distribution. I guess the other thing I should mention, are there any people that ride bike here? Bicycle riding? Okay. So this would seem to suggest if you were having a bicycle race, these are your bicycle wheels. Let's say you're the Tour de France or something like that, I don't know. It would be better to use solid wheels, not wheels where the mass is on the edge. And yet you see that everybody seems to have all the mass out on the edge. Does anyone know why that is? Well, you can make them out of some very light material, right? And again, the mass shouldn't matter, it should cancel.
Air resistance.
The wind will blow you over, exactly. You don't want to have a crosswind when you have solid wheels. It's like sails. But they do use solid wheels in indoor bicycle racing, the ones where they have the crazy teardrop helmets as well. Because if you take the crosswind out of it, then solid wheels are better. Okay. Okay, any questions on that? Okay, so that's an example. You have several homework problems just like this on your homework number 10. I'll get that posted soon. You can start on it whenever you like. Presumably, no one really wants to start on it until after the exam, so it's not up yet. Oh, okay, well then I just posted it there for those people who might be so excited that they want to start it before the exam. Okay, so the next thing, the final topic in our rotational unit is angular momentum. Why not rotational momentum? I don't know. So we have linear momentum. That's the old stuff. We never called it that because it was just momentum before. Now we call it linear momentum. Why not translational momentum? I have no idea. They're the same thing, linear and translational. And then we have angular momentum. Why not rotational momentum? I have no idea. Rotational, angular, same thing. And again, just to dispense with the annoyances and derivations, I'm just going to put down everything as a rotational analog. Okay? Momentum is mass times velocity. It's a vector. Angular momentum, what's the rotational analog to m? I and b omega, so there we have it. And we learned that if you want to change the momentum of something, you have to apply a net force for some period of time. I think I mentioned that change in momentum sometimes gets a fancy word. It's called impulse. But the point being is you have to change the momentum. If you want to change the momentum of something, you have to apply a net force for some period of time. Same thing over here. If you want to change the angular momentum, you have to, what's the rotational analog for force? Torque. And what's the rotational analog for time? Rotational time. Just kidding, it's just time. Okay? So if you want to apply angular momentum, the angular momentum change, I guess you call it an angular impulse, you have to apply net torque to something for some period of time. So, of course, this was not our primary usage for momentum. Our primary usage was when the net external force was 0. And then we could say that the momentum of the system was conserved. So we tried to find a group of objects that was relatively isolated from the outside world. We could group some objects that were essentially, for all our purposes, left alone, just bumping into each other and exchanging momentum amongst each other, amongst the members of the system, but the total momentum of the system was always conserved. So that was the beauty of momentum conservation as a method, was that all the things could bump into each other as much as they liked with a bunch of forces that were unknown in duration or strength. But all we know is that when we count up the momentum at the end for everybody, we get the same number as at the beginning. Okay? That's the same thing we're going to do here. So if we have a system where the net torque is 0, so it's relatively isolated from the outside world as far as the rotational sense. There's no outside torque trying to make it go faster or slower from outside. We expect that the angular momentum of the system should be conserved. So we should find that no matter how much the constituents of the system interact with each other, all they do is trade angular momentum amongst each other, and the total will not change. So you can notice that all the ingredients are actually familiar. In fact, all of them will be tested on your exam. We have rotational inertia, we have angular velocity, we have torque. So this is just kind of a repackaging of these quantities. And so I'm just going to kind of jump in and show you some examples where this is conserved. So my first example is going to be simple enough that it's not even going to be a system. It's going to be like one object. That's all there is to it. And that object is going to be me standing on a turntable. And the reason I say that's just one object is because I'm hoping, if all goes well, that me and the turntable will not have independent motion. I'm going to hope that I stay on it, and there I can just group it as just a single mass. And the net torque on this system is approximately 0, to the extent that I can neglect a little bit of friction that's in this pivot. So here it is. It's not a perfectly frictionless pivot, but it's going to be good enough for physics purposes. And so I should be able to get on this thing. And in the absence of a net torque, I should just stay in whatever rotational state I'm in, right? So there's obviously a little bit of frictional torque from the pivot, maybe from air resistance and things like that. But this is a highly good system where I can examine angular momentum conservation. So that means that the angular momentum of the system should be conserved in the absence of a net external torque. And let me put in the formula I omega. It looks like this. Now, if this were the linear analog, it would be very boring, because I'd have m times v would have to be conserved, and the mass doesn't usually change, right? But rotational inertia is, of course, a far more interesting quantity, because we found that it depends on not one but 3 different things. So remember that I depends on 1, 2, 3 different things. It depends on the mass. If you increase the mass, it'll increase the rotational inertia. If you take the mass further out, from the pivot, that'll increase the rotational inertia. And if you rotate it more off axis, which is to say away from the center of mass, that's another way to increase it. So I have 3 different options for increasing the rotational inertia. So I used to do number 1, but that gets a little bit dicey. I have to somehow increase my mass without exerting a net external torque. So the only way to really do that is for someone to drop some really heavy weight on me and drop it so that it would be radially acting through the hinge, so that way it wouldn't exert any torque externally. And I don't want to catch some 50-pound sandbag while I'm spinning throw my back or something. So that's been discontinued for safety reasons. The last one is also hard to pull off, because it's really hard for me to rotate my center of mass significantly away from the rotation point, because if of course, my center of mass isn't supported, I'm going to fall off. But one day I want to get some, some snowboard bindings or something to hold me on this thing, and I can lean way out off of it. But this one I can do. It's very easy to redistribute my mass. I'm going to just use these weights here as help. So we know, of course, if I take this same mass that I have and I distribute it further out, that is going to increase my rotational inertia, right? This is significantly more stubborn to rotational change than this, okay? So if I were to increase my rotational inertia, what should happen to my angular speed? Decrease. If the product has to remain the same. So let's try it. Let me make sure my pants don't fall down. That's number 1. Okay. And let's try it. Get on this thing, I'll spin. Take my arms out, and I should slow down. Yes? Okay. Works? Okay. So let's try it the other way. So let's say that instead of bringing the mass further out, I bring it further in. So if I bring my arms in my rotational inertia should what? Increase or decrease? Decrease. So that my angular velocity will increase, so my angular momentum will be conserved, right? All right, let's try that. Get on there like this. Bring my arms in. Okay, you could try that after class if you want, but it's, definitely bring your arms in gradually or you will go flying away. Okay. So that's the kind of fun you can have with just a single object. Everything was moving together, right? I can still manipulate the rotational inertia. But before I even get to having a second independent object, I do want to point out that you've seen this before.